Look up at the night sky and you'll see stars, galaxies, and distant cosmic wonders. But what if some of those breathtaking sights aren't quite what they seem? Imagine a galaxy stretched and twisted like a reflection in a funhouse mirror, its light bent and warped as it travels across the universe. This isn't science fiction, it's a real phenomenon called gravitational lensing, a cosmic illusion that tricks our eyes and reshapes our understanding of space itself. The universe, it turns out, has its own way of playing tricks on us, bending the very fabric of reality to create stunning, deceptive images in the sky. This mind-bending effect happens because massive objects like galaxies or black holes warp the space around them so profoundly that they act like giant cosmic magnifying glasses. Light from distant objects doesn't travel in a straight line when it passes these gravitational heavyweights. Instead, it curves around them, distorting and amplifying what we see. The result, a single galaxy might appear as multiple ghostly copies, or a faint, faraway star might suddenly become visible, magnified by the universe's own invisible lens. It's as if the cosmos is whispering secrets to us, revealing hidden corners we'd never be able to glimpse otherwise. But here's the real question. If gravity can twist and contort light like this, how much of what we see in the universe is truly real, and how much is just an illusion? Gravitational lensing doesn't just create surreal cosmic mirages. It also gives astronomers an extraordinary tool to study the invisible. Dark matter, mysterious black holes, even the earliest galaxies born after the Big Bang, all of them leave their fingerprints in these warped images. So buckle up, because we're about to embark on a journey to unravel one of space's greatest magic tricks, peeling back the layers of this cosmic deception to uncover the profound truths hidden within the distortions. And by the end, you'll never look at the night sky the same way again. Light has always been our window into the universe, streaming across the cosmos in what seems like perfect, unwavering straight lines. But Einstein's groundbreaking theory of general relativity flipped that intuition on its head. He revealed that space isn't just an empty stage where light travels undisturbed. It's more like a vast, stretchable fabric, warped and dimpled by the weight of massive objects. Picture a bowling ball sitting on a trampoline. The heavier the ball, the deeper the dent it creates. Now imagine rolling a marble across that same trampoline. Instead of moving in a straight line, the marble curves along the dip created by the bowling ball. That's exactly what happens to starlight when it journeys past galaxies or black holes. The fabric of spacetime bends under their immense gravity, and light, like the marble, follows the curves rather than cutting through cleanly. This cosmic bending doesn't just distort light's path, it reshapes our entire perception of the universe. Before Einstein, scientists assumed light was untouchable, zipping through space without any detours. But general relativity showed that gravity isn't just a force pulling objects together. It's the very curvature of spacetime itself. The denser the object, the sharper the bend, and the more dramatic the illusion. A galaxy cluster, for instance, can twist background light into surreal rings or split a single quasar's image into multiple mirage-like copies. These aren't flaws in our telescopes or tricks of the eye. They're the universe revealing its hidden mechanics, proving that even something as seemingly straightforward as a beam of light dances to the tune of gravity's invisible hand. What's truly remarkable is how this idea transformed astronomy. Suddenly, scientists realized they could use these distortions like a celestial magnifying glass. When light bends around a massive object, it doesn't just warp, it amplifies, brightening distant stars and galaxies that would otherwise be too faint to see. It's as if the universe handed astronomers a natural telescope, one built into the fabric of spacetime itself. And that revelation didn't just confirm Einstein's wildest predictions. It opened doors to discovering the invisible, from dark matter's ghostly grip to the earliest flickers of light after the Big Bang. The straight lines we once took for granted are anything but, and that bend in the light, that's where the real magic happens. Einstein's genius reshaped our understanding of gravity, but even he underestimated one of his own predictions. When he first calculated that massive objects could bend light like a lens, he dismissed it as little more than a mathematical curiosity, a fleeting quirk of his equations with no real-world application. In his own words, he called the effect not observable because the alignment needed between a distant star, a foreground object, and Earth would be so precise, so astronomically rare, that catching it in action seemed impossible. The universe, it appeared, was playing hard to get, but science has a funny way of surprising even its greatest minds. Decades later, astronomers began spotting strange distortions in the sky, galaxies stretched into arcs, quasars mirrored like reflections in a cosmic funhouse. These weren't flaws in their observations, they were the very phenomena Einstein had scribbled down and then shelved. The irony, his unobservable prediction had become one of astronomy's most powerful tools. What changed the sheer scale of the cosmos? While Einstein imagined a single star bending light from another, astronomers soon realized entire galaxy clusters, with their unimaginable mass, could warp spacetime on a grand scale, magnifying and distorting the light of objects billions of light-years behind them. The shift in perspective was profound. Instead of dismissing gravitational lensing as a cosmic oddity, scientists began calling it Einstein's telescope, a natural observatory built into the fabric of the universe itself. It's almost poetic, the same theory that once seemed too abstract to matter, now lets us peek into corners of the cosmos we could never reach otherwise. Dark matter's gravitational grip, the formation of the first galaxies, even the elusive nature of black holes, all of them leave traces in these warped beams of light. Einstein might have doubted his idea's usefulness, but the universe, it turns out, had other plans. And in the end, his hesitation only makes the discovery sweeter, a reminder that even the brightest minds can't always see the full picture until the cosmos decides to reveal it. For nearly half a century, Einstein's prediction about bent light remained just that, a prediction. Then, in 1979, astronomers stumbled upon something extraordinary while studying a quasar nearly 9 billion light-years away. At first glance, it appeared to be two identical quasars sitting suspiciously close together in the sky, flickering in perfect unison. Twin cosmic beacons separated by just 6 arcseconds, a distance so tiny it defied the odds. How could two distinct quasars, blazing with the energy of 1 trillion suns, behave so identically? The answer was as elegant as it was revolutionary. They weren't two objects at all. Closer scrutiny revealed the truth. A massive galaxy, invisible in optical light but detectable through its gravity, sat directly between Earth and the distant quasar. Like a cosmic prism, the galaxy's immense weight bent the quasar's light around it, splitting the single object into mirrored images. This was the twin quasar, officially known as Q0957 plus 561 A and B, the first confirmed case of gravitational lensing in action. The implications were staggering. Here was direct proof that spacetime itself could distort light, just as Einstein had theorized 6 decades earlier. What once seemed like an impractical mathematical abstraction was now etched across the heavens. The discovery didn't just validate Einstein, it unveiled a new way to explore the universe. Astronomers realized that lensed objects weren't just scientific curiosities, they were cosmic breadcrumbs, revealing the presence of otherwise invisible mass. The galaxy causing the twin quasars split images, for instance, wasn't bright enough to see directly, but its gravity betrayed its existence. This hidden orchestrator, warping light from behind it, became one of the first clues that the cosmos was filled with dark matter, an unseen scaffolding shaping everything we observe. Suddenly, the universe's greatest illusions became its most honest informants, exposing secrets no telescope could capture alone. and the twin quasar was just the beginning. Once scientists knew what to look for, the sky seemed to crackle with these gravitational mirages. Galaxy clusters sculpted distant light into glowing arcs. Einstein's rings, while stars in our own Milky Way briefly magnified the light of others behind them, like celestial flashlights flickering on. Each distortion mapped the invisible, turning the fabric of spacetime into a cosmic detective tool. What began as an accidental discovery in 1979 blossomed into an entire field of astronomy, proving that sometimes the universe's greatest truths are hidden in plain sight, if you know how to decode the illusions. Let's break down this cosmic magic trick piece by piece. Picture a galaxy cluster, a sprawling family of hundreds of galaxies bound together by gravity sitting between us and a more distant object, say, a quasar burning brightly billions of light years away. As the quasar's light journeys toward Earth, it doesn't just sail past the cluster unimpeded. Instead, the immense gravity of all that clustered mass warps the very fabric of spacetime around it, like a bowling ball resting on a stretched sheet. The light, compelled to follow this curved space, bends around the cluster instead of traveling straight. This bending isn't uniform. The edges of the galaxy cluster tug at the passing light differently than its core, creating a complex gravitational landscape. Depending on where the light passes closer to the center or skirting the outskirts, it can split into multiple paths, like a fork in an invisible cosmic road. When these diverging beams finally reach us, they paint an astonishing picture. The single quasar might appear as 2, 3, or even a shimmering ring of duplicate images, each a ghostly echo of the same source. These aren't random smudges in telescope data. They're precise, calculable mirages arranged by gravity's invisible hand, but the real marvel lies in the magnification. Just as a glass lens focuses sunlight into a bright spot, the gravitational pull of the galaxy cluster can intensify the distant quasar's light. Regions of spacetime where the bending is strongest act like cosmic magnifying glasses, amplifying faint objects we'd never detect otherwise. This is how astronomers glimpse some of the universe's most elusive residents, fledgling galaxies from the dawn of time, or the faint glow of stars orbiting supermassive black holes. The cluster isn't just distorting the light, it's enhancing it, turning whispers of the cosmos into shouts we can finally hear. The details get even wilder when we zoom in. Sometimes a single star within the lensing galaxy cluster, or even a lone black hole, passes directly in front of a background star. For a fleeting moment, its gravity acts like a microscopic lens, briefly brightening the distant star's light in a phenomenon called microlensing. These events are cosmic winks lasting days or weeks, but they reveal otherwise invisible objects, rogue planets, neutron stars, or the faintest dwarfs drifting between galaxies. What's striking is how predictable these illusions are. By mapping the warped images and measuring their distortions, astronomers can reverse engineer the lens's mass, including the dark matter we can't see. It's like deducing the shape of a hidden object by studying its shadow. Every stretched arc, every mirrored quasar is a clue etched in light waiting to be decoded. So while these cosmic mirages might trick our eyes at first glance, they're actually the universe's way of showing us the truth, one bent photon at a time. The universe doesn't just bend light in one uniform way, it plays with gravity's grip like an artist experimenting with different brushes, each stroke leaving a unique imprint on the canvas of the sky. The most dramatic of these cosmic distortions is strong lensing, where the gravitational pull of a massive object like a galaxy cluster is so intense that it twists background light into unmistakable arcs or even perfect rings. Picture a distant galaxy stretched into a luminous crescent, or a quasar mirrored into multiple identical copies arranged symmetrically around a central lens. These are the universe's grand illusions, visible proof of spacetime's curvature on a colossal scale. Einstein himself predicted these Einstein rings, but even he might have been stunned to see how crisp and intricate they appear in modern telescope images. These aren't just pretty cosmic quirks, they're precise tools. By measuring the exact shape and position of these arcs, astronomers can map the distribution of mass in the lensing cluster, including the elusive dark matter that leaves no other trace. Then there's weak lensing, the universe's subtler sleight of hand. Instead of dramatic arcs, weak lensing gently warps the shapes of countless background galaxies, like a heat haze distorting the view on a desert horizon. The effect is so slight that no single galaxy appears obviously altered, but when scientists analyze thousands of them, patterns emerge. Imagine holding up a pane of frosted glass. Individual objects blur, but the overall warping reveals the glass's imperfections. Weak lensing works the same way, exposing the large-scale structure of the cosmos. It's how we've traced the cosmic web, the vast network of dark matter filaments connecting galaxy clusters like invisible threads. Unlike strong lensing, which relies on rare, precise alignments, weak lensing paints a broader portrait of the universe's hidden architecture. But gravity's light-bending tricks aren't limited to grand scales. Enter microlensing, where a single star or even a rogue planet can briefly amplify the light of another star passing behind it. These events are fleeting, sometimes lasting just hours or days, but they're cosmic gold mines. Because microlensing doesn't depend on the lens being bright, it unveils objects we'd otherwise never spot. Orphan planets drifting between stars, black holes lurking unseen, or faint red dwarfs too dim to detect directly. It's like the universe momentarily flicking on a flashlight, illuminating secrets in the dark. In 2011, microlensing helped astronomers spot a planet over 13,000 light-years away, nearly halfway to the galactic center. Proof that even the tiniest gravitational nudges can have outsized revelations. What's fascinating is how these three flavors of lensing complement each other. Strong lensing reveals the detailed mass of individual clusters, weak lensing traces the universe's large-scale skeleton, and microlensing hunts the hidden inhabitants of our galactic neighborhood. Together, they turn gravity into a universal translator, decoding messages written in warped light. Whether it's a star's fleeting glow or a galaxy stretched into a smile, each distortion is a clue, a reminder that the cosmos is far more dynamic, more deceptive, and more dazzling than it first appears. Of all the cosmic illusions born from gravitational lensing, few are as striking or as eerily perfect as the Einstein ring. Named for the physicist who first imagined their existence, these celestial halos appear when a distant galaxy, quasar, or star aligns precisely behind a massive foreground object like a galactic bullseye. The result, a circle of light so flawless it looks hand-drawn, as if some cosmic artist traced it with a compass. But this isn't artistry, it's pure physics. The foreground galaxy's gravity bends the background object's light evenly in all directions, warping it into a luminous loop that encircles the lens like a fiery wedding band. One of the most famous examples gleams in the constellation Fornax, where a galaxy called H01447+239 weighs in with the gravitational heft of 2 trillion suns. Its immense pull distorts the light of a far more distant galaxy directly behind it, stretching that faint glow into a near-perfect ring nearly 40,000 light-years across. What's astonishing isn't just the ring's symmetry, it's the time warp it represents. The light we see from the lensing galaxy left its stars just 5 billion years ago, while the warped ring's glow began its journey a staggering 10 billion years in the past. In a single image, we're witnessing two snapshots of cosmic history folded together by gravity's invisible hand. The science behind these rings reveals even more magic. For an Einstein ring to form, the distant light source, the lensing mass, and Earth must align with near mathematical precision, like threading a needle across billions of light years. Even a slight misalignment smears the ring into an arc or breaks it into multiple images, which is why perfect rings are rare cosmic gems. But when conditions are just right, the ring's size and brightness become cosmic measuring tapes. Astronomers can calculate the mass of the foreground galaxy down to the last star, including the dark matter halo that would otherwise stay hidden. What's wilder still? Some Einstein rings aren't static. In 2021, the Hubble Space Telescope spotted a ring so warped it appeared to flicker over time. The reason? The lensing galaxy wasn't alone. It had a supermassive black hole companion whose shifting gravity acted like a funhouse mirror, twisting the ring's shape as it orbited. This dynamic lensing gave scientists a live-action view of spacetime's flexibility, proving that even these seemingly serene rings are alive with motion. So the next time you see an image of an Einstein ring, remember, you're not just looking at a pretty cosmic quirk. You're seeing gravity's blueprint, a temporary alignment so precise it turns the universe itself into a lens, revealing galaxies too faint, too distant, or too ancient to witness any other way. And somewhere in that glowing halo, light from the early universe is still bending, still traveling, still whispering secrets across the eons. Galaxies don't just decorate the cosmos, they serve as some of the most powerful telescopes ever built. Take the Hubble Frontier Fields, a project that turned 6 massive galaxy clusters into cosmic magnifying glasses, pushing the limits of how far we can see into the early universe. These clusters are so dense, so packed with matter, both visible and dark, that they warp spacetime into natural lenses, amplifying the faint glow of galaxies billions of light years behind them. It's like using a magnifying glass to focus sunlight, except here, the universe itself bends the light, revealing galaxies so distant they existed when the cosmos was just a fraction of its current age. One of these clusters, Abell 2744, nicknamed Pandora's cluster, is a gravitational powerhouse. Its tangled web of galaxies and dark matter creates such extreme lensing that background galaxies appear stretched into long, luminous arcs, some magnified by up to 30 times their normal brightness. Without this cosmic zoom lens, those galaxies would be invisible to even our most advanced telescopes. But thanks to the cluster's gravity, we're catching glimpses of infant galaxies forming just 500 million years after the Big Bang, a time when the universe was still shaking off its primordial darkness. The frontier fields didn't just stop at magnification, they unveiled an entire hidden population of ultra-faint galaxies, far smaller and more numerous than anyone expected. These tiny, dim objects are the building blocks of today's grand spirals and ellipticals, and without lensing, we'd have no way to study them. It's like discovering an ancient city buried underground, except instead of ruins, we're uncovering the first bricks of cosmic structure. What's truly groundbreaking is how these natural telescopes reveal the invisible scaffolding of the universe. By mapping the distorted shapes of background galaxies, astronomers can trace the distribution of dark matter within the lensing clusters. The arcs and smears aren't random. They're precise fingerprints of gravity's influence, allowing scientists to reconstruct the cluster's mass down to the finest detail. In some cases, the lensing effect is so strong that it creates multiple images of the same galaxy, each taking a slightly different path around the cluster. By comparing these mirror images, researchers can even measure the expansion rate of the universe itself, but the frontier fields are just the beginning. Upcoming telescopes like the James Webb Space Telescope and the Nancy Grace Roman Space Telescope will team up with these cosmic lenses to peer even further back in time. Imagine a future where we're not just spotting the first galaxies, but watching them ignite their earliest stars flickering to life in the darkness of the young cosmos. Thanks to gravitational lensing, the universe's grandest illusions are also its most generous gifts, bending light not to deceive us, but to reveal truths we'd otherwise never see. And with each new observation, we're not just looking deeper into space, we're traveling further back in time, uncovering the story of how everything we know came to be. Gravitational lensing doesn't just bend light, it exposes the universe's best-kept secret, dark matter. Think about it like this. When astronomers measure the distortions caused by a galaxy cluster's gravity, they often find something bizarre. The amount of visible matter, stars, gas, dust simply can't account for the extreme warping they observe. It's as if an invisible giant is pressing down on the cosmic trampoline, bending spacetime far more than the visible objects suggest. That missing mass, that's dark matter's calling card, its gravitational grip betraying its presence even though it emits no light, reflects no signal, and slips through our telescopes undetected. Take the famous bullet cluster, for example. This cosmic collision, 730 million light-years away, shows two galaxy clusters that have smashed through each other like phantom trains. Here's the eerie part. The visible matter, hot gas glowing in X-rays, lagged behind during the collision, slowed by friction. But the lensing maps reveal the bulk of the mass kept moving ahead unbothered. Why? Because dark matter doesn't interact with light or ordinary matter the way gas does. It sailed through the crash unscathed, dragging spacetime with it. The lensing distortions didn't follow the glowing gas. They traced the invisible mass, painting a ghostly outline of dark matter's true distribution. It's one of the most direct proofs that dark matter isn't just a theoretical placeholder, it's real, it's massive, and it shapes the cosmos in ways visible matter alone never could. But lensing does more than confirm dark matter's existence. It lets us map its hidden architecture. When light from distant galaxies passes through a cluster, the subtle warps in their shapes reveal how dark matter is distributed, down to the finest filaments of the cosmic web. Some clusters show dark matter clumped in smooth, diffuse halos, while others have sharp, dense cores. These differences hint at dark matter's mysterious properties. Is it cold, moving sluggishly and clumping easily? Or warm, with particles zipping through space fast enough to resist tight packing? Lensing provides the clues, and sometimes the observations get even weirder. In galaxy cluster Abell 520, astronomers found a dark core, a region where lensing indicated a huge concentration of mass, but with almost no visible matter or even dark matter's expected gravitational effects. It's like finding a footprint with no foot, a shadow with no object to cast it. These anomalies force scientists to reconsider dark matter's behavior, or even question if gravity itself works differently on cosmic scales. What's remarkable is how lensing turns the universe into a dark matter detector. No lab on Earth can catch these elusive particles, but out in space, their gravity writes messages in the light of distant galaxies. Every stretched arc, every duplicated quasar is a breadcrumb leading us deeper into the dark. And with each new observation, we're not just mapping the invisible, we're decoding the hidden rules of the cosmos, one warped photon at a time. If dark matter is the universe's hidden skeleton, then weak gravitational lensing is the tool that lets us trace its invisible contours. Projects like the Dark Energy Survey have turned this subtle cosmic trick into a precision instrument, scanning vast swaths of the sky to reconstruct dark matter's shadowy architecture in 3 dimensions. Picture a cosmic cartographer painstakingly mapping an unseen realm, not with ink or pixels, but by measuring the faint warping of millions of distant galaxies. Their distorted shapes, twisted ever so slightly by the gravity of intervening dark matter, reveal where the invisible mass lurks and how it's woven into the fabric of the cosmos. The Dark Energy Survey, a collaboration spanning hundreds of scientists and 6 years of observations, didn't just glance at the sky. It stared deep, capturing images of over 300 million galaxies across 1/8 of the visible universe. Each galaxy's light traveled billions of years to reach us, bending as it passed through dark matter's gravitational field along the way. The distortions are minuscule. Some galaxies appear just 1% more elongated than they should, but by averaging these tiny deflections across countless galaxies, patterns emerge. The result, a 3-dimensional tomographic map. peeling back layers of the universe to show dark matter's distribution across cosmic time. It's like listening to whispers echoing across a canyon. Individually, they're faint, but together they reveal the canyon's shape. What these maps expose is astonishing. Dark matter isn't scattered randomly. It forms an intricate cosmic web, with dense knots where galaxy clusters nest and wispy filaments stretching between them like invisible bridges. Some regions are nearly empty, vast voids where dark matter's grip is faint, while others are so packed with mass they warp spacetime into natural telescopes. The dark energy survey's maps even hint at how this web evolved, showing how dark matter's tendrils grew denser over billions of years as gravity pulled them into the universe's grand scaffolding. But the survey's revelations go beyond structure. By comparing the lensing maps with the observed positions of galaxies, scientists found something puzzling. Dark matter's distribution is slightly smoother, slightly more spread out than predicted by our best cosmological models. This discrepancy, though subtle, could shake our understanding of how dark matter behaves, or even how gravity operates on cosmic scales. Is dark matter clumpier than we thought? Are there unknown forces at play? The maps don't answer these questions outright, but they're guiding astronomers toward new mysteries, proving that even our most advanced tools can't fully pierce the dark. The real triumph of these projects lies in their ambition. They're not just cataloging dark matter, they're chronicling the universe's growth, tracing how invisible mass shaped everything from the first galaxies to the sprawling superclusters we see today. And with next-generation telescopes like the Vera-C, Rubin Observatory poised to map billions more galaxies, these shadowy blueprints will only grow sharper, revealing the universe's hidden framework in ever greater detail. The dark may be elusive, but thanks to the universe's own gravitational lens, we're learning to see the unseeable, one warped galaxy at a time. Peering into the universe's infancy is like trying to read a faded letter from the edge of time. The light from those first galaxies is so faint, so stretched by cosmic expansion, that even our most powerful telescopes strain to see it. But gravitational lensing changes the game. By turning massive galaxy clusters into natural zoom lenses, it gives us a fighting chance to glimpse the cosmic dawn, a time when the first stars and galaxies flickered to life in a pitch-black universe. These lensed images aren't just snapshots, they're time machines, bending not just light but our very understanding of how everything began. Take MAX 0647 plus 7015, a galaxy cluster so massive it warps spacetime into a colossal lens. Behind it lies MAX 0647JD, a galaxy so distant its light has traveled 13.3 billion years to reach us. Without the cluster's gravitational boost, this galaxy would be a barely detectable smudge. But lensing magnifies its light multiple times over, revealing details astronomers could never have seen otherwise: clusters of newborn stars, pockets of primordial gas, even hints of the first heavy elements forged in stellar furnaces. This isn't just observation, it's archaeology on a cosmic scale, sifting through the universe's oldest layers. What makes these lensed galaxies so special isn't just their distance, it's their purity. The early universe was a fundamentally different place, with simpler, smaller galaxies devoid of the complex structures we see today. They burned hotter, brighter, and bluer, fueled by pristine hydrogen and helium, untouched by the chemical enrichment of later generations of stars. Lensing lets us study these galactic infants in unprecedented detail, catching them in the act of forming their first stars, some at rates hundreds of times faster than our Milky Way today. One such lensed galaxy, nicknamed the Sunburst Arc, shows clusters of stars so young and dense they're essentially fossilized snapshots of star formation's violent beginnings. But the real surprise, how many of these early galaxies lensing has revealed. Before Hubble's Frontier Fields project, theorists predicted the early universe would host a handful of large, bright galaxies. Instead, lensing uncovered a teeming population of tiny, faint ones galaxies 100 times smaller than the Milky Way, yet blazing with star formation. This population explosion forced astronomers to rewrite their models of cosmic dawn, suggesting that small galaxies, not massive ones, were the true building blocks of everything we see today. The most breathtaking lensed galaxies even hint at the universe's very first light. In 2018, astronomers spotted a candidate galaxy, MAX 1149 JD1, whose light may have begun its journey just 250 million years after the Big Bang. It's a wisp of a thing, magnified by a foreground cluster into visibility, but its existence pushes the boundaries of how soon galaxies could form after the universe's birth. If confirmed, it would mean stars ignited earlier and in greater numbers than anyone imagined, a revelation that could rewrite the timeline of cosmic evolution. Lensing doesn't just magnify these ancient galaxies, it stratifies them, because light from different parts of a lensed galaxy takes slightly different paths around the foreground cluster. We effectively see multiple epochs of its life at once. One mirrored image might show the galaxy as it was a few million years earlier or later than another, like flipping through a cosmic flipbook of its infancy. This temporal layering lets astronomers watch galactic evolution in a way no simulation could match, tracing how these early systems grew, merged, and eventually gave rise to the universe we know today. The implications stretch beyond astronomy. By studying the chemistry of these lensed galaxies, scientists have found traces of the first heavy elements carbon, oxygen, silicon, spewed into the cosmos by early supernovae. These elements became the raw material for planets, life, and us. In a very real sense, gravitational lensing isn't just showing us the past, it's revealing our own cosmic lineage, tracing the atoms in our bodies back to their primordial origins. With next-generation telescopes like the James Webb Space Telescope teaming up with these natural cosmic lenses, we're on the verge of an even greater leap. Soon we may capture the moment the first stars switched on, ending the universe's so-called dark ages and flooding the cosmos with light for the very first time. Gravitational lensing, once a curious prediction of Einstein's equations, has become our ultimate time machine, and the early universe's secrets are just starting to come into focus. Gravitational lensing doesn't just warp light, it bends time itself. When a distant object's light splits into multiple images due to a foreground galaxy's gravity, those mirrored photons don't all arrive at Earth simultaneously. Some take slightly longer paths around the cosmic lens, creating delays that can stretch days, months, or even decades. It's as if the universe handed scientists a stopwatch to measure the cosmos's expansion, with each delayed image serving as a ticking hand on a celestial clock. One of the most striking examples is the double quasar Q0957+561. Though its twin images appear side by side in the sky, one arrives 420 days later than the other. The reason: the light creating the second image had to travel a detour, an extra 1.1 light-years around the lensing galaxy's gravity well. That delay isn't just a curiosity, it's a precise tool. By comparing the time difference with the quasar's known brightness fluctuations, astronomers calculated the Hubble constant, the rate at which the universe expands, with unprecedented accuracy. These delays reveal more than just distances. In the case of supernova Gravitational, astronomers witnessed something extraordinary. A single exploding star reappear 4 times in different positions around a galaxy cluster, with each image delayed by months or years. By tracking these staggered arrivals like echoes in a cosmic canyon, scientists reconstructed the cluster's hidden mass distribution, including dark matter's gravitational footprint. The supernova's light acted like a probe, mapping spacetime's curvature in 3 dimensions. What's mind-bending is how these time gaps expose the universe's accelerating expansion. Light from delayed images has traveled a slightly longer path through an ever-stretching cosmos, meaning the space between its photons expands more than light taking a shorter route. By measuring how much these delays grow over time, astronomers can test whether dark energy, the mysterious force driving cosmic acceleration, changes strength across eons. It's like reading the universe's pulse through its gravitational illusions. The wildest implication: some lensed objects might flicker in our skies right now as delayed light finally reaches us. Ghosts of events that technically already happened, their light trapped in gravity's labyrinth until the cosmos decides to reveal them. Every warped image isn't just a snapshot, it's a time capsule carrying secrets from moments we'd otherwise never witness. And with each tick of these cosmic clocks, we're not just observing the universe, we're decoding its rhythm. In December 2015, astronomers witnessed something that defied all expectations: a supernova that refused to fade away. Nicknamed Gravitational after the Norwegian astrophysicist who first theorized such an event, this stellar explosion did something unprecedented. It reappeared in the sky not once, but 4 separate times, each appearance separated by months. The reason: a massive galaxy cluster, max Joan 149.3 plus 2223, had bent spacetime so severely that it split the supernova's light into multiple paths, each taking a different cosmic detour before reaching Earth. It was as if nature itself had set up a celestial experiment, offering scientists a rare chance to test the very fabric of the universe. What made Gravitational so extraordinary wasn't just its multiple appearances, it was the precision with which astronomers could predict them. Using detailed maps of the galaxy cluster's mass, including its invisible dark matter halo, researchers calculated exactly when and where each new image of the supernova would emerge. When the final mirrored image flickered into view right on schedule in late 2015, it was a triumph. The universe's gravitational lens had acted like a perfectly tuned clock, confirming not just Einstein's theories but our ability to decode the cosmos's hidden blueprints. But Gravitational's true gift was even deeper. Each delayed image carried a time stamp, a record of how long its light had been stretched and bent by the cluster's gravity. By comparing these delays, astronomers could measure the Hubble constant, the rate at which the universe expands, with a new level of independence from other methods. The results were revelatory. While most techniques for calculating the Hubble constant fall into 2 camps with stubbornly different answers, Gravitational's lensed light offered a third, gravity-driven perspective. Its value landed tantalizingly between the others, hinting that the solution to cosmology's biggest ongoing debate might lie in these cosmic time delays. The supernova also exposed secrets about the lensing cluster itself. The exact timing and brightness of each mirrored image revealed subtle variations in the distribution of dark matter, showing how it clumped and curved spacetime in ways invisible to traditional telescopes. Some paths through the cluster were slightly more congested with matter, slowing the light's journey like cars navigating a crowded highway. Others were smoother, allowing photons to zip through with less resistance. These tiny divergences painted a high-resolution map of the cluster's hidden structure, one where dark matter's gravitational fingerprints were finally made visible. Perhaps most mind-bending is what Gravitational's reappearances imply about our view of the cosmos. If a single supernova can echo across years due to lensing, how many other cosmic events might be out there, their light still winding its way through gravity's maze? Every warped image we spot could be part of a staggered sequence, fragments of the same story arriving out of order. It's a reminder that the universe doesn't just show us its history, it filters it through spacetime's wrinkles, delivering the pieces on its own schedule. And with each lensed replay, we're not just watching the past, we're decoding the very mechanics of reality. Gaze at any star in the night sky and you might wonder, does it host planets too faint for our telescopes to spot? For most of history, that question seemed impossible to answer. But gravitational microlensing has cracked the cosmic code, revealing worlds orbiting stars thousands of light years away by the faintest gravitational whispers. Here's how it works. When a distant star aligns perfectly with a foreground star, the nearer star's gravity acts like a magnifying glass, briefly brightening the background star's light. Now imagine that foreground star has a planet. As the planet orbits, its own tiny gravitational tug adds a second, smaller bump to the light curve, a telltale blip betraying its presence. This technique has uncovered some of the most exotic planets ever found. Take Ogle 2013 BLG0341, a frigid world 6 times Earth's mass circling its star at nearly the same distance Jupiter orbits our Sun. Without microlensing, we'd never have spotted it. The planet's host star is so dim it's practically invisible. Yet for 2 hours in 2013, its gravity warped starlight just enough to leave a fingerprint. What's astonishing is how sensitive this method can be. Some microlensing planets induce light variations as subtle as 1%, like detecting a firefly's shadow flickering across a searchlight from 10,000 miles away. The real power of microlensing lies in its reach. While other planet hunting techniques favor stars relatively close to Earth, microlensing probes the galactic bulge, the densely packed core of our Milky Way, where stars and potential planets swarm like fireflies in a jar. In 2022, astronomers announced the discovery of a rogue planet floating freely between stars, untethered to any solar system. Microlensing caught its momentary gravity flicker as it drifted through the galaxy, proving these nomadic worlds might outnumber stars in our galaxy. But microlensing doesn't just find planets, it weighs them. The duration and shape of the light curve reveal the planet's mass, while the star's magnification pattern clues us into its orbit. Some systems, like Ogle 2006 BLG 109, even showcase 2 planets simultaneously distorting the same background star's light, offering snapshots of entire solar systems in miniature. The future of this technique is even more thrilling. Projects like the Nancy Grace Roman Space Telescope will monitor hundreds of millions of stars for microlensing events, potentially uncovering thousands of new worlds, including Earth-mass planets in the habitable zones of dim red dwarfs. These discoveries could rewrite the galactic census, proving planets aren't the exception but the rule, scattered across the cosmos like breadcrumbs in gravity's grand labyrinth. Every subtle flicker of starlight isn't just data. It's a message from the dark, reminding us the universe hides its treasures in plain sight, waiting for the right moment to bend the light and reveal itself. A quasar is one of the most luminous objects in the universe, a supermassive black hole devouring matter so violently it outshines entire galaxies. Now imagine that brilliant beacon not as a single point of light, but as 2, 4, or even 5 identical copies scattered across the sky like celestial echoes. This isn't a glitch in reality, it's gravitational lensing at its most dramatic, where a massive foreground galaxy or cluster splits the quasar's light into multiple paths, each bending around the cosmic lens before reaching us. The result, a single quasar multiplied, its clones arranged in perfect symmetry around the lensing mass like a cosmic mirage. These multiplied quasars aren't just eerie curiosities, they're Rosetta Stones for decoding the universe's deepest mysteries. Take the Einstein cross, a stunning quartet of quasar images encircling a foreground galaxy. The 4 luminous dots aren't separate objects, they're the same quasar, its light cleaved by the galaxy's gravity into distinct beams. Each image takes a slightly different route around the lens, meaning they arrive at Earth at slightly different times. Some photons race ahead on a straighter path, while others lag behind after navigating deeper bends in spacetime. This time delay isn't just poetic, it's a forensic tool. When the quasar flickers, the change appears in each image days or weeks apart, letting astronomers measure the Hubble constant, the universe's expansion rate, with precision. But the real magic lies in what each cloned image reveals. Because each path around the lens grazes different parts of the quasar's structure, the images vary subtly in brightness and color. One might highlight the quasar's blazing accretion disk, the swirling maelstrom of superheated gas spiraling into the black hole, while another captures faint emissions from its outer jets. It's like inspecting a gemstone under multiple lights. Each angle reveals new facets. In some cases, the lens even acts like a cosmic prism, smearing the quasar's light into a spectrum that exposes the composition of interstellar gas billions of light years away. The most extreme examples push lensing to its limits. The quasar SDSS-J1004+4112 doesn't just split into multiple images, it's stretched into a full Einstein ring, a fiery halo encircling the lensing galaxy. Here, the alignment is so perfect that the quasar's light bends uniformly in all directions, forming a continuous loop. Yet even this flawless ring holds secrets. Minute kinks in its structure betray the presence of dark matter clumps within the lensing galaxy, invisible masses too small to detect any other way. What's astonishing is how these multiplied quasars serve as cosmic laboratories. By comparing the brightness of each image, astronomers can map the quasar's accretion disk in unprecedented detail, resolving features smaller than a light year across. In one groundbreaking study, flickers in a lensed quasar's images revealed the disk's turbulent vortices, swirls of plasma heated to millions of degrees, spinning just beyond the black hole's event horizon. Without lensing, these details would blur into an unresolved speck. Yet perhaps the most profound implication is what these mirages say about spacetime itself. When we see a quasar's light split into multiple images, we're witnessing gravity's grip on reality, proving that the universe doesn't just contain space and time. It is space and time, a dynamic fabric that bends, stretches, and folds under the weight of matter. Each mirrored quasar is a reminder that the cosmos is far stranger, far more malleable than our eyes alone can perceive. And as astronomers discover more of these gravitational mirages, they're not just collecting pretty pictures, they're assembling an atlas of the unseen, one bent photon at a time. Gravitational waves, ripples in space-time generated by cataclysmic events like colliding black holes, have already revolutionized astronomy. But what if these cosmic tremors could be lensed, bent, and magnified by massive objects just like light? The implications would be extraordinary. Picture a gravitational wave from a distant black hole merger passing near a galaxy cluster. As the cluster's gravity warps space-time, the wave could split into multiple signals, each arriving at Earth at slightly different times. The result, a cosmic echo chamber where a single collision plays back in staggered whispers, revealing secrets about the universe's hidden structure. The first tantalizing hint that this might be possible came in 2019, when the LIGO-Virgo collaboration detected a gravitational wave event named JW190521. Its signal showed peculiar distortions, almost as if the waves had been subtly lensed on their journey. While the evidence wasn't conclusive, it opened the door to a wild possibility that gravitational waves like light could be bent by gravity itself. If future observatories catch a strongly lensed gravitational wave, one split into clear, time-delayed copies, it will be akin to hearing the same cosmic drumbeat from multiple directions, each note carrying clues about the lensing object's mass and composition. But the real prize lies in what lensed gravitational waves could tell us about the fabric of spacetime. Unlike light, gravitational waves barely interact with matter, slipping through galaxy clusters and dark matter halos unimpeded. Any distortion in their signal wouldn't stem from gas or dust, but purely from the warping of spacetime itself. This means lensed waves could map the universe's gravitational fields with unmatched precision, exposing the true distribution of dark matter. No indirect inferences required. Imagine weighing a galaxy cluster not by how it bends distant starlight, but by how it contorts the passage of a gravitational wave. the measurements could settle debates about dark matter's nature. Is it cold and slow-moving or warm and diffused? The waves wouldn't just hint at the answer, they'd declare it. Even more thrilling is the prospect of probing extreme gravity regimes. When a gravitational wave skirts the edge of a black hole's event horizon, the spacetime curvature is so intense that subtle effects, like quantum corrections to Einstein's gravity, might imprint on the lensed signal. If those fingerprints exist, lensed waves could uncover physics beyond general relativity, testing whether black holes truly behave as predicted or hide surprises in their deepest gravitational wells. It's like using the universe's most violent events to scan its most enigmatic corners, a cosmic biopsy of spacetime's true nature. The challenge, detecting these lensed signals, requires next-generation observatories with unprecedented sensitivity. Projects like the Einstein telescope and LISA, a space-based gravitational wave detector, could spot the faint, delayed echoes of lensed waves, especially from mergers in the early universe. Some theorists speculate that the first galaxies, born in a cosmos far denser than today's, might have lensed gravitational waves so severely that their signals arrive garbled, like a voice echoing through a maze. Untangling those distortions could reveal the universe's infancy in a way light never can, offering a soundtrack to accompany our deepest images of cosmic dawn. But perhaps the most profound implication is temporal. Just as lensed light lets us see multiple epochs of a galaxy's life at once, lensed gravitational waves could deliver signals from the same event across years or even centuries. A black hole collision observed today might replay again in 2030, its waves taking a slower detour around a massive lens. These time-staggered signals would act as universal clocks, measuring the expansion of space itself between their arrivals. If dark energy's strength has changed over cosmic history, the wave's delays would betray it, a smoking gun for one of cosmology's greatest mysteries. We're standing at the edge of a new frontier where gravity's whispers and warps converge. Lensed gravitational waves wouldn't just be a curiosity, they'd be a paradigm shift, turning spacetime's ripples into a diagnostic tool for everything from dark matter to quantum gravity. The universe has spent billions of years bending light to show us its illusions. Soon, it might bend spacetime itself to reveal its truths. And when that day comes, we won't just be listening to the cosmos, we'll be decoding its deepest rhythms. Gravitational lensing isn't just a tool for astronomers, it's also captured the imagination of storytellers, weaving its way into films and TV shows that bring cosmic wonders to life. Take Interstellar, Christopher Nolan's visually stunning masterpiece where the phenomenon takes center stage. Remember the spine-tingling moment when the crew approaches Gargantua, the film's fictional supermassive black hole. The black hole's gravity bends light so dramatically that the surrounding accretion disk appears as a luminous halo, warped into a perfect circle above and below the void. This wasn't just artistic flair. Nolan worked with physicist Kip Thorne to render the black hole's lensing effects with scientific accuracy, down to the distorted starlight flickering around it. The result, a jaw-dropping visualization that made Einstein's equations feel tangible and introduced millions to the mind-bending reality of spacetime's curvature. But Interstellar isn't the only pop culture touchstone playing with lensing. The sci-fi series The Expanse uses it more subtly, with characters referencing lensed quasar images as navigation markers in the void between stars. Even video games like Destiny 2 incorporate lensed galaxies as skybox art, their arcs and rings hinting at unseen cosmic giants lurking in the background. These creative nods matter because they do something textbooks can't. They make gravitational lensing visceral. When audiences see a black hole's gravitational grip twisting light into a ring, or hear characters debate the optics of a lensed star, abstract physics becomes something you can almost feel. The fascination isn't just about spectacle, it's about relatability. Lensing taps into a universal human curiosity. What if our eyes deceived us? That's why films and games love to riff on it. In Contact, Jodie Foster's character watches a distant star's light bend around a wormhole, a moment that mirrors real lensing while teasing the idea of cosmic shortcuts. Even superhero stories like Doctor Strange borrow lensing's visual language, folding cities into kaleidoscopic arcs that echo the warped galaxies astronomers study. These portrayals, whether rigorous or stylized, spark something primal. They remind us that the universe is stranger than fiction, and that the illusions we see in the sky are gateways to deeper truths. What's especially compelling is how pop culture gets the science wrong, and why that's okay. Most films exaggerate lensing for drama, showing black holes bending light instantly or warping entire star fields like funhouse mirrors. In reality, the distortions are far subtler, requiring precise alignments and painstaking observation. But these creative liberties serve a purpose. They're gateway drugs to real science. After Interstellar debuted, searches for gravitational lensing and Einstein rings spiked. Teachers reported students asking how to calculate a black hole's shadow. The film didn't just entertain, it turned astrophysics into a conversation starter. The ripple effect extends beyond screens. Sci-fi authors like Alastair Reynolds and Lou Sixon weave lensing into their plots, using it to magnify alien signals or hide cosmic anomalies. These stories flirt with a tantalizing idea. What if advanced civilizations use lensing, intentionally aligning stars and black holes to create interstellar communication networks? It's speculative, sure, but it's rooted in real science. Astronomers have pondered whether lensing could amplify signals from distant exoplanets, or if alien megastructures might exploit natural lenses to beam messages across galaxies. Perhaps the most enduring legacy of lensing in pop culture is its democratization of wonder. You don't need a PhD to gasp at Gargantua's glowing halo or to ponder the mirrored quasars in the expanse. These moments invite everyone, gamers, movie buffs, casual stargazers, to ask big questions. Could lensing reveal hidden dimensions? Might we one day decode lensed light from the universe's first stars? By blending science with storytelling, filmmakers and writers haven't just popularized gravitational lensing, they've turned it into a shared language for cosmic curiosity. And in doing so, they've reminded us that the universe's greatest magic tricks aren't just for scientists. They're for anyone who's ever looked up and wondered what else is out there and what illusions might be hiding it. Unraveling the universe's gravitational mirages isn't as simple as pointing a telescope at the sky and snapping a photo, one of the biggest hurdles astronomers face. Telling the difference between a genuinely lensed object and a galaxy that just looks weird. Take the case of Hannes Voorwerp, a strange green blob spotted in 2007. At first glance, its eerie glow and distorted shape made it a prime lensing candidate until closer inspection revealed it was actually a cloud of gas illuminated by a quasar's long-dead light, a cosmic fossil rather than a gravitational illusion. Misidentifications like this aren't just academic stumbles, they send researchers down rabbit holes, wasting precious telescope time chasing phantoms. The challenge gets even thornier with rare galactic oddities. Some galaxies naturally warp into arcs due to tidal forces during collisions, mimicking lensing's signature stretch. Others, like the Tadpole Galaxy, flaunt long tails of stars that could easily be mistaken for lensed streams. Even supernova remnants or jets from active black holes can masquerade as lensed features. The solution: cross-examination. Astronomers now rely on multiple wavelengths, X-rays to spot hot gas, infrared to pierce dust, radio to trace cold hydrogen, to build a forensic profile of each candidate. If the supposed lens lacks the mass to warp light, or if the background object turns out to be foreground noise, the case falls apart. But spotting the illusion is only half the battle. Decoding it demands computational muscle that would have been unimaginable just decades ago. Every lensed system is a unique puzzle, with distortions shaped by the lens's mass distribution, including the invisible dark matter. Reverse engineering these warps requires running thousands of simulations, each tweaking variables like dark matter clumpiness, galaxy cluster density, and even the universe's expansion rate. The more intricate the lensing effect, say, a quasar split into 4 images with time delays, the more computing power it devours. Projects like the Hubble Frontier Fields consumed millions of CPU hours, with supercomputers crunching data for weeks to reconstruct a single cluster's hidden mass. And then there's the noise. Earth's atmosphere blurs ground-based images, while cosmic rays and instrument glitches litter space telescope data with false signals. Even the James Webb Space Telescope's stunning lensing revelations require painstaking cleanup, with algorithms scrubbing away artifacts that could masquerade as warped galaxies. The faintest lensed objects, those primordial galaxies from the universe's dawn, often flirt with the detection threshold, their signals drowned in the cosmic static. Separating these whispers from the noise is like listening for a single violin in a symphony of static. Yet perhaps the most overlooked challenge is time itself. Strong lensing events depend on near-perfect alignments, and the universe is anything but static. Galaxy clusters drift, stars within them orbit, and the cosmic expansion stretches the lensing geometry over eons. A perfectly aligned system today might be a dud in a million years, or vice versa. Some of the most tantalizing lensed candidates sit in that frustrating gray zone, their distortions too subtle to confirm without years of follow-up observations. It's a reminder that studying the cosmos means playing by its timescales, not ours. Despite these obstacles, each hurdle crossed reveals just how much lensing has to teach us. Every misidentified oddity sharpens our classification tools. Every computational bottleneck broken unlocks new ways to map dark matter. And every painstakingly cleaned image brings us closer to those faint, warped whispers from the edge of time. The challenges aren't roadblocks, they're the price of admission to the universe's grandest magic show, where the tricks are real and the secrets hidden in plain sight. Every night, telescopes around the world capture millions of images of the sky, a flood of data so vast it would take astronomers centuries to sift through by eye. Hidden in that cosmic haystack are gravitational lenses, rare alignments that could unlock secrets of dark matter or reveal the universe's first galaxies. The problem, finding them, is like spotting a single bent straw in a field of hay. But now, artificial intelligence is turning this needle in a haystack search into a treasure hunt, scanning the heavens with superhuman speed and precision to uncover lensed objects we'd otherwise miss. Take the Dark Energy Survey, which imaged 300 million galaxies. Traditional methods flagged around 12,000 potential lenses, but when researchers fed the same data to a machine learning algorithm called Deep Lens, it uncovered hundreds of additional candidates, including bizarre arcs and rings human eyes had overlooked. The AI didn't just match astronomers' efforts, it surpassed them, spotting subtle distortions in galaxy shapes that even seasoned experts might dismiss as noise. How? By training on thousands of simulated lenses, the algorithm learned to recognize gravity's fingerprints in ways no human brain ever could, detecting patterns too faint or complex for our visual cortex to process. The real game changer is scale. Projects like the Vera-C, Rubin Observatory's legacy survey of space and time, will scan the entire southern sky every few nights, generating terabytes of data nightly. No team of humans could keep up, but neural networks thrive in this deluge. A recent breakthrough involves unsupervised AI, which doesn't even need pre-labeled examples to find lenses. Instead, it teaches itself to spot anomalies, flagging anything that breaks the expected symmetry of galaxies. This approach already led to the discovery of an Einstein ring so pristine it looks like a celestial halo, lurking unnoticed in decades-old archival data. But AI's role isn't just discovery, it's interpretation. Once a lensed object is found, machine learning models reconstruct the hidden mass distribution of the foreground lens, teasing apart dark matter's contribution from visible stars and gas. Some algorithms can even predict how lensed images should flicker over time, helping astronomers schedule follow-up observations. In one case, an AI predicted the reappearance of a lensed supernova to within 4 days, a feat akin to forecasting an eclipse's timing based on a single snapshot of the moon's orbit. The implications stretch beyond astronomy. The same techniques used to decode cosmic mirages are now helping diagnose diseases from medical scans or identify rare species in satellite imagery. It's a reminder that the universe's greatest puzzles often spark tools that transform life on Earth. And as AI grows more sophisticated, who knows what other illusions, what other truths might come into focus. The sky's distortions are no longer just mysteries. They're data points waiting to be decoded by silicon minds as curious as our own. The next decade of astronomy promises to revolutionize our understanding of gravitational lensing, thanks to a new generation of telescopes designed to peer deeper into the cosmos than ever before. Leading the charge is the James Webb Space Telescope, already rewriting the rules of what's possible. With its infrared eyes, Webb can see through cosmic dust that obscures lensed galaxies in visible light, revealing warped snapshots of the universe's first billion years. In its first year alone, Webb uncovered lensed galaxies so ancient their light had stretched into infrared wavelengths invisible to Hubble galaxies that existed when the universe was just 2% of its current age. But Webb isn't just spotting these cosmic mirages, it's dissecting them. By analyzing the spectra of lensed galaxies, Webb can measure their chemical composition, star formation rates, and even the temperature of their interstellar gas, all through the universe's natural magnifying glass. Then there's the Vera-C, Rubin Observatory's legacy survey of space and time, or LSST, set to transform lensing into a large-scale science. Unlike targeted missions, LSST will scan the entire southern sky every few nights for a decade, creating a time-lapse of the cosmos that could catch millions of lensing events. Imagine spotting a distant supernova flicker into view, then watching as its light splits into multiple images over weeks or months, each delayed by the gravity of an unseen galaxy cluster. LSST Wide Field Camera will catch these cosmic dominoes in action, turning the sky into a dynamic map of spacetime's wrinkles. The survey's real power lies in weak lensing. It'll measure the subtle warping of billions of galaxy shapes, constructing a 3D dark matter map spanning 8 billion light-years. But the future doesn't stop there. The Nancy Grace Roman Space Telescope, launching later this decade, will combine Webb's sensitivity with a field of view 100 times larger than Hubble's. Roman's specialty, hunting for primordial lenses, galaxies so young they were still assembling when the universe was in its infancy. By finding these early lenses, Roman could reveal how dark matter clumped in the cosmos's first chapters, testing whether our models of cosmic evolution hold true. One of its key targets will be orphan lensed images, ghostly duplicates of galaxies with no obvious lens in sight, potentially betraying the presence of invisible dark matter halos floating between galaxies. Meanwhile, on the cutting edge, the European Space Agency's Euclid mission is already mapping the geometry of the dark universe with precision. Euclid's razor-sharp optics can distinguish between a galaxy's natural shape and the subtle stretching caused by foreground dark matter, allowing it to measure the universe's expansion history with unprecedented accuracy. Its first images revealed thousands of previously unknown lensed galaxies, some warped into hair-thin arcs by clusters so massive they defy conventional physics. And looming on the horizon is the Square-Kilometre Array, a radio telescope network so sensitive it could detect lensed gravitational waves, ripples in space-time bent by massive galaxy clusters. If successful, it would open an entirely new window on lensing, one where we see not with light but with the vibrations of space-time itself. What unites these missions is their ability to turn lensing from a rare curiosity into a routine tool. Soon, astronomers won't just stumble upon Einstein rings, they'll catalog them by the thousands, tracking how their shapes shift over years to measure dark matter's microscopic movements. We'll watch as lensed supernova replay like cosmic reruns, their staggered arrivals clocking the universe's expansion in real time. And perhaps most thrillingly, we might uncover lenses so ancient they magnify the very first stars, their light twisted but not yet extinguished, carrying whispers from the dawn of creation. The universe's greatest illusions are about to become its sharpest lenses, and through them, we'll see farther, deeper, and clearer than ever before. Of all the cosmic coincidences gravitational lensing relies on, none are more extraordinary than the moments when Earth, a massive lensing object, and a distant background source align with near mathematical precision. These ultra-rare convergences, where the 3 points form a near straight line across billions of light years, create magnification so extreme they can boost a single star's brightness 10,000 times over. Imagine a celestial searchlight suddenly flipping on, illuminating cosmic details otherwise lost in the dark. One of the most striking examples unfolded in 2018, when astronomers witnessed a solitary blue giant star named Icarus, formerly known as Max J1149+2223 lensed star 1, briefly become the most distant individual star ever observed. Normally, detecting a lone star at 9 billion light-years would be impossible, its light far too faint. But a fortuitous galaxy cluster acted as nature's ultimate zoom lens, aligning so perfectly that it amplified Icarus's glow to detectable levels. The magnification arose from a double cosmic jackpot. Not only was the star directly behind the cluster's densest knot of dark matter, but a single sun-sized star within the cluster also happened to pass directly along the line of sight. This microlens within a macro lens created a temporary focusing effect, like sunlight passing through a magnifying glass held over a curved mirror. For 70 days, Icarus burned brighter than entire galaxies in its neighborhood, offering an unprecedented look at the life cycle of an ancient cosmic giant. What makes these perfect alignments so valuable isn't just their magnification power, it's the surgical precision they offer. When the alignment is flawless, light from the background object wraps around the lensing mass in what's called a caustic curve, an area where magnification spikes to staggering levels. Any slight deviation from perfection, say, the background star drifting a hair's width off axis, would smear the light into unrecognizable distortions. But when the geometry is exact, the caustic acts like a cosmic microscope, resolving details otherwise lost to distance. During Icarus's magnification event, astronomers could measure the star's surface temperature and infer its size, despite it being halfway across the observable universe. It was like reading the engraving on a coin from 10,000 miles away. The implications stretch beyond stellar studies. In 2022, another perfect alignment revealed a star system from the universe's first billion years, a pair of nascent stars nicknamed Earendel and its fainter companion. Here, the lensing galaxy cluster's curvature stretched their light into long arcs, preserving spectral fingerprints of pristine hydrogen and helium, elements untouched by later generations of supernovae. These snapshots of Population 3 stars, the hypothesized first generation of stars, are cosmic time capsules, offering clues about how the earliest light sources ended the universe's dark ages. Without these fleeting alignments, we'd have no way to study such fragile, distant relics. Yet the rarest alignments tease even grander possibilities. Theoretical models suggest that under perfect conditions, a lensed object could form an Einstein cross, of 4 distinct images arranged symmetrically around the lens while simultaneously sitting on a caustic curve. The result, a single object appearing 5 times in one image, 4 magnified copies plus the central, ultra-brightened caustic version. Such an event hasn't been observed yet, but with next-generation telescopes scanning wider swaths of sky, it's only a matter of time before the cosmos serves up this quintuple cosmic illusion. These alignments are more than just lucky breaks. They're temporary windows into realms we're not meant to see. Like a detective finding a single fingerprint in a vast crime scene, astronomers wait patiently for these moments when the universe's geometry conspires to reveal its secrets. And with each new alignment, the cosmos reminds us, sometimes the most profound truths come into focus only when everything lines up just right. Could the universe's gravitational mirages be hiding something even stranger, signs of other universes brushing up against our own? It's a wild idea, but some theoretical physicists have begun exploring whether certain lensing anomalies, those that defy conventional explanations, might be cosmic breadcrumbs leading to a multiverse. Picture this: a galaxy cluster bends light so severely that it creates multiple images of a distant quasar, but the brightness and positions of those images don't quite match what Einstein's equations predict. Normally, astronomers would tweak their models of dark matter or consider unseen substructures. But what if the discrepancy isn't just missing mass? What if it's the gravitational fingerprint of a parallel universe tugging at ours from an unseen dimension? The concept hinges on brane cosmology, a fringe but mathematically elegant theory suggesting our universe is a three-dimensional brane, floating in a higher dimensional space, like a sheet of paper suspended in a vast room. Other branes' parallel universes could drift nearby, their gravity weakly leaking into ours. In this scenario, a neighboring brane's gravitational pull might subtly alter how light bends around massive objects in our own universe, creating lensing patterns that appear slightly off. One hypothetical example involves shadow galaxies, phantom masses detected only through lensing distortions, with no visible matter to account for them. Could these be reflections of stars and gas from a sister universe, warping spacetime just enough to leave ghostly imprints in our sky? The most tantalizing and controversial evidence comes from the so-called cold spot, a puzzling region in the cosmic microwave background where temperatures dip unexpectedly. Some theorists argue it could be the bruise of a collision with another universe, its gravitational echoes lingering in the cosmos like ripples from a stone tossed into a pond. If true, lensing distortions near this anomaly might carry subtle signatures of that primordial crash, perhaps an unexplained warp in the light of background galaxies, or a cluster whose mass distribution doesn't align with its lensing effects. Of course, mainstream cosmology remains deeply skeptical. Most lensing anomalies have plausible explanations within our current understanding of dark matter and galaxy formation. The multiverse hypothesis, while thrilling, slides dangerously close to unfalsifiability, the scientific sin of proposing an idea that can't be tested. Yet the allure persists because lensing, at its core, is about decoding gravity's whispers. And if gravity can leak between branes, as some string theorists suggest, then the universe's grandest illusions might not just be tricks of light. They could be cracks in reality itself, fleeting glimpses of a cosmos far vaster than we ever imagined. For now, these ideas linger at the edge of science, more thought experiment than theory. But as telescopes grow sharper and lensing catalogs swell, astronomers might stumble upon distortions so bizarre they demand radical explanations. Whether those explanations lead to parallel universes or simply new physics, one thing's certain: the universe's gravitational hall of mirrors still has surprises in store, and the next one could rewrite reality as we know it. When we peer at a lensed galaxy stretched across the sky, are we seeing the universe as it truly is, or just a funhouse mirror's warped reflection? It's a paradox at the heart of gravitational lensing. The very distortions that reveal hidden cosmic truths also manipulate reality before our eyes. Take the twin quasar, its light split into mirror images by an invisible galaxy. Those duplicated beams aren't just scientific data. They're literal optical illusions, photons tricked into taking scenic routes across spacetime. Does that mean lensing deceives us, or does it peel back deeper layers of reality that straight-line light could never expose? Consider how artists use concave mirrors to create surreal portraits, faces stretched into dreamlike elongations. The distortions aren't lies, they reveal how light bends under specific conditions, teaching us about optics and perception. Gravitational lensing operates similarly. A lensed Einstein ring might look nothing like the original galaxy, but its warped shape encodes precise information about the lensing mass's distribution, including dark matter's invisible grip. The distortion isn't obscuring truth, it's encrypting it. Like a cryptographer deciphering a scrambled message, astronomers use mathematical models to undo the lensing effect, reconstructing the background object's true form while simultaneously mapping the foreground's hidden structure. Far from cheating our understanding, lensing gives us two truths for the price of one: the undistorted source and the distorting lens. Yet some distortions defy easy unraveling. When the galaxy cluster Abell 371 warps a distant supernova into a radiant cross, the time delays between its images create a cosmic jigsaw puzzle. The supernova's real brightness becomes meaningless. What we observe is a patchwork of magnified and delayed fragments. Here, lensing doesn't just alter our view, it fractures time itself, showing us the same event at multiple stages simultaneously. Is this a distortion of reality or an expansion of it? Perhaps lensing doesn't deceive so much as democratize perspective, offering several angles on cosmic events that would otherwise be visible from just one. Philosophers might argue that all observation is distortion. Even the light from an unlensed star is altered by interstellar dust, redshifted by cosmic expansion, smeared by Earth's atmosphere. Lensing merely makes these manipulations visible, turning the universe's subtle curations into glaring headlines. In that sense, it's the ultimate honesty, a reminder that every astronomical image is processed by nature long before it reaches our telescopes. The real illusion isn't the warped galaxy, it's the belief we ever saw the cosmos unfiltered. What settles the debate is utility. If lensing were pure deception, it couldn't consistently predict phenomena like supernova reappearances or reveal independently verifiable dark matter maps. Yet it does both with astonishing precision. The distortions behave like a cipher with a key, not a hall of mirrors designed to mislead. When the James Webb Space Telescope studies a lensed galaxy from the cosmic dawn, its warped light isn't obscuring the past, it's amplifying whispers we'd otherwise never hear. So perhaps the question isn't whether lensing cheats, but how it redefines truth. In a universe where gravity sculpts spacetime itself, maybe reality was always plural, a tapestry of perspectives waiting to be unwoven. The light that bends around a black hole isn't lying, it's telling a different story about the shape of space. And in those contorted beams, we don't lose our grasp on cosmic truth. We gain new ways to hold it. Ever wanted to play cosmic detective, sifting through telescope data to uncover hidden gravitational mirages? Thanks to projects like Zooniverse's space warps, you don't need a PhD in astrophysics to contribute to groundbreaking discoveries, just curiosity and an internet connection. This isn't just busy work, it's real science. Every year, telescopes capture millions of images of the sky, far more than professional astronomers could ever analyze alone. That's where citizen scientists step in, scanning these cosmic snapshots for telltale arcs, rings, and duplicate galaxies that hint at lensing. And the results speak for themselves. Volunteers have already identified hundreds of previously unknown lensed systems, some of which have led to published research papers. The process is surprisingly intuitive. Platforms like Space Warps train users to recognize the subtle signatures of lensing. Maybe it's a faint blue smudge stretched into a smile around a galaxy cluster, or a trio of identical red dots arranged just a little too symmetrically to be coincidence. You're not just clicking buttons, you're honing an eye for cosmic patterns, learning to distinguish genuine gravitational mirages from optical tricks or camera artifacts. It's like solving a puzzle where the pieces are scattered across billions of light years, and your clicks help stitch them back together. What makes these projects so powerful is the human advantage. While algorithms can scan data quickly, they often struggle with ambiguity. A slightly warped galaxy might stump a computer but leap out to a human observer. In one notable case, a volunteer spotted a peculiar arc in an image that algorithms had dismissed as noise. Turned out to be a rare double lens, where two galaxy clusters aligned along the same line of sight, warping a background galaxy into an intricate pretzel shape. Discoveries like these prove that curiosity can't be fully automated, but the impact goes beyond cataloging curiosities. Every lensed galaxy flagged by a citizen scientist becomes a new data point in our understanding of dark matter, cosmic expansion, and galaxy evolution. Some volunteers have even co-authored scientific papers, their names listed alongside professional researchers, proof that the thrill of discovery isn't reserved for those in lab coats. Projects like Hubble's Hidden Treasures or the Dark Energy Survey's citizen science portals offer similar opportunities, inviting anyone to mine raw telescope data for unseen wonders. The beauty of these initiatives lies in their accessibility. Whether you're a student, a retiree, or someone with 15 minutes to spare on a lunch break, you're contributing to the same quest that once occupied Einstein's pen and paper calculations. And who knows, the next time you log in, you might be the first pair of eyes to spot a lensed quasar from the universe's adolescence, or a warped galaxy revealing dark matter's fingerprints. The cosmos is full of illusions waiting to be uncovered, and sometimes all it takes to find them is a fresh perspective. Gravitational lensing isn't just a tool, it's a revolution in how we see the universe. From unmasking the invisible grip of dark matter to amplifying the faintest whispers of the cosmic dawn, this phenomenon has reshaped our understanding of reality itself. Think about it, without spacetime's bending light like a funhouse mirror, we'd have no way to weigh galaxy clusters, no window into the universe's first galaxies, no proof that dark matter isn't just a mathematical placeholder but a tangible force sculpting the cosmos. Every warped quasar, every stretched galaxy, every shimmering Einstein ring is a testament to Einstein's wildest idea that space and time aren't just a stage for the universe's drama, but active participants, twisting and curving under the weight of matter. And the revelations keep coming. Lensing has exposed rogue planets drifting between stars, caught supernova replaying like cosmic echoes, and even hinted at physics beyond Einstein's equations. It's turned the universe into a laboratory where gravity's illusions aren't distractions. They're breadcrumbs leading us to deeper truths, the most astonishing part. This isn't futuristic tech or speculative theory. It's happening right now in real time as light from distant stars bends around invisible masses on its way to your eyes. So next time you gaze at the night sky, remember, what you're seeing might be a cosmic sleight of hand. That flickering star could be magnified by an unseen black hole. That smudge of a galaxy might be stretched into a faint arc by dark matter's pull. The universe is full of tricks, but thanks to lensing, we're learning to see through the illusion, to decode the hidden messages written in warped light. The greatest show isn't just above us, it's in the very fabric of space, bending reality to reveal secrets we're only beginning to grasp. Look up, what you see might not be what's